Fluids, buoyancy, and Archimedes' principle. Questions to ponder. Why do I feel lighter when I'm in a pool? Why is it easier to lift things when they are submerged? How much does the water rise when I get in the bathtub? To take a look at buoyancy, we first need to recall that pressure varies at different depths. So if we had an object here submerged in a fluid, then what we know from before is that the pressure at the bottom of the object, P2 here, is greater than the pressure at the top of the object, because these relative pressures, these gauge pressures, are dependent on the various depths here. Since the bottom is deeper, it has more pressure than the top of the particular object here. So now we'll have a chance to look at the buoyant force. The buoyant force is created by that pressure difference from the top to the bottom of a submerged object. Since the pressure is greater at the bottom, if the areas are equal here, top and bottom, if the pressure at the bottom is greater than the pressure at the top, then the force at the bottom of the object is greater than the force at the top of the object. Therefore, that difference in force is what creates what we call the buoyant force. And from before, we know that that forces here can be calculated by taking the pressure on the surface times that surface area. So this overall force down here pushing upward is P2 times A2, and the pressure of the liquid pressing down on the top of this object is P1A1. That's the force, rather. And therefore, if we plug into our pressure, our two different gauge pressures here, then what we find out is we can get this final equation here, that the buoyant force is equal to the density of the liquid times gravity times the area times the change in depth. Of course, what we see here is that this really, that area times this height, is really the volume of this object. So we get a general equation for buoyant force, and that is the density of the liquid that it's submerged in times the acceleration due to gravity times the volume of the object that is being submerged. And there we have it. We have the buoyant force. Booyah! I have an ant here, and you may wonder if it's a male or a female ant. Well, we actually have a way to tell. We can take that ant and place it in this dish of water and see what happens. Notice that the ant is floating. Therefore, we know that it is a buoyant.
You are so dumb. You are really dumb. For real.
Yeah, that was kind of dumb. I apologize. Hey, but this problem isn't dumb. This is our first buoyancy calculation. So read the problem, do your best to calculate, and when you're done, come on back to the video and see how you did. So how did you do? Hopefully you started off with your buoyancy formula here, and you realize that this is the density of water that you use, because it's the water that's supporting this bar of gold here, the volume of the bar of gold. So when you plug in the numbers, something that may have dawned on you is that, wow, that's a pretty tiny force. But you have to realize that that little teeny bar of gold is a pretty tiny volume. So you wouldn't get much buoyant force on that gold. To get a better sense of buoyancy, the University of Colorado has made some great simulations. So now it's your time. Now it's time for you to pause the video here and open up a new tab in your browser. Type in PhET simulations and buoyancy. Choose the first one there, I think is University of Colorado that you'll find, and run that simulation on buoyancy. And I think you'll have a better feel once you have done that. So, now that you played around with buoyancy a little bit, one of the great discoveries regarding buoyancy is Archimedes' principle. Archimedes discovered that the buoyant force on a body immersed in a fluid is equal to the weight of the fluid that is displaced by the object. So if we have a cylinder here filled with water, and we put inside of it this object, this other cylinder, this object, we place that down inside. Now this object is more dense than the water is, so it's going to sink. So what we do is we attach it to a spring here, and that spring is going to give an upward force. Now if there was no water in this container, if there were no water in this container, then there would be no buoyant force, and the spring would simply be measuring the weight of this object down here. When we have the cylinder here filled with water, and we submerge this other cylinder, this object that's more dense, what we see is the water will rise. Not only will the water rise, but the amount of force in the spring will decrease by a certain amount. How much that force decreases is called the buoyant force. What Archimedes realized is that the amount of volume that the water rose here, if we could take that out and look at it over here, and we take its mass times acceleration due to gravity, that weight of that water would be equal to the buoyant force on the object. Pretty cool discovery.
Now, you may have heard of the story about Hero, the newly elected king of Syracuse, Greece, and the fact that he had hired a goldsmith to manufacture a crown for him. And he had heard rumors that the goldsmith actually put some silver in with the gold that he had given him to make the crown. And he was very furious about that, but didn't know how to determine if the crown was really made of gold or silver. So he went to his cousin, Archimedes, who was 22 at the time, but still a very renowned mathematician and physicist, and asked Archimedes, is there a way to tell if the crown is really gold or if it does have some silver in it? And Archimedes pondered and pondered that thought and was deep in thought and decided to relax a little bit to see if he could come up with a solution. And so Archimedes went to the public baths that they had in Greece there. And he noticed that when he went into a tub in the baths, that the water rose, in fact, spilled out over the edge of the baths. And that made him think, hey, I wonder if the amount of water that was spilling out over the bath was that amount of weight, if that's how he could tell the density of that particular crown. And so it dawned on him, and he thought about it, and he thought, yes, this is the correct solution. And so the story goes that he yelled, because he was so excited, he yelled Eureka at his discovery by thought. Now, the story was pretty accurate up to that last little part. See, what really happened is he had this thought, and he was very excited, and he was getting ready and to get out of the baths to dry off, and two heathens who hadn't bathed in weeks came in to get into the baths and went by them. And that's when he said, ooh, Eureka.
Yeah, sometimes my jokes kind of reek a little bit, so apologize for that. Here's a problem that'll challenge you a little bit with buoyancy, and so why don't you give this a try and check out the difference in how much the rock weighs and the volume of the rock to find out the density of the liquid that it's submerged in. So give this a go and pause the video. When you come back to the video, we'll see how you did. Good luck. So let's start off with our force equation here when we have submerged objects. And when we do that, we know that the force is going to be a little bit less that we have to hold up this object because it'll be supported by this buoyant force. In this particular case, We know what the force is that we feel. That's the 270 newtons. And we know the weight of the rock before it was submerged. The only thing we don't know is the buoyant force. So kind of rearranging things here, in other words, subtracting the buoyant force from both sides and then subtracting this force from both sides, we end up with this equation. So if we simply take the difference here and what the rock would have weighed and then what the rock weighs when it's submerged, we can see that the buoyant force is the difference there, or 50 newtons. We also know that that buoyant force is equal to the density of the fluid that it's submerged in times gravity times the volume of the object that's submerged, in this case the rock. So knowing that, we can solve for the density of the fluid by dividing both sides by acceleration due to gravity and the volume. So doing that and then switching sides here, we end up plugging in all of our numbers. Oh yeah, this is also a little bit of a catch here, a little trick. This was in centimeters cubed, and so we have to really kind of divide by a million here, because it's a centimeter is 1/100th of a meter, and it's in 3 dimensions, so 100 times 100 times 100 ends up moving the decimal over 6 decimal places, and so moving it over 6 decimal places, we can get our answer in meters cubed, and we need that to balance the units out here. And so we plug all this information in, crank it out, and we get 924 kilograms per meters cubed. Notice that that's a little less dense than water, which is 1,000, and in fact I got that number to create the problem. That's the density of vegetable oil, and that's your problem. So hopefully we can answer these questions now. Why do I feel lighter when I'm in a pool? Why is it easier to lift things that are submerged? And how much does the water rise when I get into a bathtub? And Scratch's parting idea. And you'll never sink if you're always striving for continuous improvement.